look at Clausius inequality. So we have seen that by Clausius theorem, delta Q by T for a reversible process is equal to ds. So we again and again we have mentioned that this is only valid for a reversible process. So what happens if we have an irreversible process or a more generic process or a more general process? So processes that occur in the real world are never reversible. They are always irreversible because it has degradation associated with it. So what can we say about irreversible processes? So this is addressed by the Clausius inequality. So if we consider two heat engines, one being reversible, another being irreversible, operating between the same temperature or operating between the same source and sink, supposing that we won't assume anything. So operating between the same source and sink, we already know that by Carnot theorem, the efficiency of the reversible heat engine is always greater than the efficiency. We are talking about thermal efficiency. The thermal efficiency of the reversible heat engine is always greater than the efficiency of thermal efficiency of a irreversible heat engine. So eta R is greater than eta. Okay, so we know these things. Thermal efficiency of the reversible heat engine is always greater than the thermal efficiency of irreversible heat engine, and from the absolute temperature scale we know something like this, that is delta Q1 by T1 for a reversible process. This is a general statement, is equal to delta Q2 by T2 for a reversible process. That is what the absolute temperature scale, or the definition of absolute temperature scale, is that delta Q1 by delta Q2 is equal to T1 by T2. So this is what we had defined as the absolute temperature. And that is, the absolute temperature scale should satisfy the condition that for any reversible cycle that is operating between two fixed source and sink, the heat supplied, the ratio of heat supplied should be equal to the ratio of the temperatures. That was the criteria for defining absolute temperature scale. So we know this, and we know from Clausius theorem that we had defined entropy. Okay, so we'll apply these things. So we'll first take the efficiency term. So efficiency can be written as W, the work done by the heat input Q in. So the work done is obviously Q out minus Q in, Q in minus Q out by Q in. So this gives 1 minus Q out by Q in. So for both cases, I'll just substitute the values for Q out and Q in. So Q2 represents the heat rejected, Q1 represents, this is delta. Forgive me. So this is delta Q1R. So anyway, I've just substituted the value for the efficiency. So here we have negative term. One will get cancelled out. Negative term. We'll switch the signs. So when I switch the signs, I'll get something like an equation which can be used, or which is very similar to that of what we defined for the absolute temperature scale. That is, for a reversible cycle, we can replace the heat ratios of heat by the absolute temperature ratios. So we replace it, T2 by T1. So what we get is something like this, that is delta Q2 by T2 should be greater than delta Q1 by T1, or delta Q1 by T1 should be less than delta Q2 by T2, or we'll get something like this, that is delta Q1 by T1 plus minus of delta Q2 by T2 is equal to is less than 0. This is from the inequality that we have here. So this represents, again, the negative sign represents a heat rejected. So if we apply this, this is for a system that takes in heat in a process 1 and rejects heat in a process 2. So if we apply this to a continuous process, we can replace this for like with cyclic integral. So for a cyclic integral, we'll get cyclic integral delta Q by T should be less than 0 for any generic process, for any arbitrary continuous generic process. Okay, so the thing is 0, we already defined delta Q by T for reversible process is equal to 0. So we have just replaced the 0 with cyclic integral delta Q by T or cyclic integral of ds. Okay, so this is called as the Clausius inequality. This is an equation. We'll just look into what Clausius inequality is. So we have two equations, that is cyclic integral delta Q by T is less than 0 and cyclic integral of delta Q by T for reversible process is equal to 0. We'll combine this and write something like this: cyclic integral of delta Q by T is less than or equal to cyclic integral of ds, which is equal to 0. Cyclic integral of ds is equal to 0. Or for in the differential form, delta Q by T for any arbitrary process can be reversible or irreversible. It is less than or equal to ds. For any arbitrary process, reversible or irreversible, I can write integral from a to b delta Q by T is less than or equal to integral from a to b ds. Okay, so to qualify when these inequalities hold, so if we have a reversible process, the equality sign will hold, and if we have an irreversible process, it will be the less than sign. Okay, the thing that we have to look into is the sign will never be positive, or cyclic integral of delta Q by T will never be greater than 0, or cyclic integral of delta Q by T will never be greater than ds. The integral of delta Q by T will never be greater than the integral of, or will never be greater than delta S. Okay, so just clarifying things. So what does this mean? So this means that the ratio delta Q by T1 will be equal to the ratio of delta Q2 by T2 in case of a reversible process. But in case of an irreversible process, this is not. In case of an irreversible process, delta Q2 by T2, which is the heat transferred at lower temperature, this ratio will be higher than the heat transferred at higher temperature, that is at T2.